Moving on, we're going to look at the choice of waveforms. What would be a good choice of waveforms? And we're going to look at the binary case. Now, we've saw in the first section when we looked at the linear sampling receiver and match filter that we could, as long as we chose the match filter to match the signal waveform, that we had free choice of the signal waveform. Then we went to our second part, which is looking at the signal space analysis. And now we have a way of representing each one of the signals in symbols in signal space. What I'd like to show you now is just to take the binary case and to look at the impact of two choices of waveforms. And these two choices of waveforms, very simple, very easy to understand, will give very different results on performance. And so this will inform us on one of the reasons why there are so many different types of modulation formats, because some have better, some have worse performance, but better characteristics in other regards. So we'll be discussing that now, first time in the binary case. So the two cases we're going to look at are called on-off keying, with an acronym of OOK, and the other one is called antipodal signaling, which will also be known as BPSK, or binary phase shift keying. Many names for basically the same waveforms, but in any case, this subject we're discussing now is covered in section 3.2 of the Scholar textbook. So we're going to be focusing on performance, and the performance we're going to be evaluating in this case is bit error rate. And the bit error rate is calculated based on the noise statistics. So again, it's always important to look at the noise, understand the probability density there, in order to be able to calculate the bit error rate. So we've seen that the noise is represented in a vector form. The elements of this vector are zero mean Gaussian noise. They're independent, and we have the probability distribution for the noise, which is given by this total probability. Now we're going to look at the antipodal cases, two binary cases. The first is called antipodal, the second one is called on-off keying. And I said they're very simple. So in one case, let's define one of the waveforms to be something that is a constant A during the time interval of a symbol. So a rectangular pulse. So here's some amplitude A. Starts at 0, goes to the time of a symbol, or a symbol in this case a bit. Now that's one waveform, and that's going to be the same for both of these. And I'll call that the logical one. In the antipodal signaling, what I choose to do is that for the logical 0, I'm going to send the negative of this. So it's also what we call bipolar. So instead of being A, it would be minus A. In on-off keying, completely different choice, I choose to send nothing for a logical 0. When there's a logical 0, I will send no voltage at all. Okay, so different strategies. You know, which one would be better or worse? How do we decide better or worse? What's a fair comparison? Those are the questions that we're going to be answering now as we examine these two very simple choices. So we could use the Gram-Schmidt process to find the basis function for instance, let's take the antipodal case. And the Gram-Schmidt process would say, take the first symbol, this one, and the only thing I do is normalize the area. So right now the area under the curve is AT, and I want the area under the curve to be 1. So, I'm sorry, when it's squared, it would be A squared of T, would be the, for SI squared. So in this case, I'm going to divide by A, the square root of T, in order to normalize this waveform so that it has unit energy, not area under the curve, but under the square of the curve. And therefore, I would change this amplitude. Instead of being A, it would be 1 over the square root of T, and this would be for the basis function. Now, of course, the first step in the Gram-Schmidt process, if I applied it to case 2, would be exactly the same, because they have the same first. So they both have the same first basis vector. And if I go on with the Gram-Schmidt process and I went for the second basis vector, it would be 0, right? Because S logic 0 is just -1 times the first one. So clearly I stopped the Gram-Schmidt process here, and of course the logic 0 here is 0, so the Gram-Schmidt process would stop. So in this case it is a one-dimensional, a 1D vector space for both the antipodal and for the Onoff keying, and it has the same basis vector. Okay, so it's going to make the comparison a little easier because we have the same basis in both cases. So what are the coefficients in this basis? Well, the first symbol is basically the original, but I have to multiply it so that the amplitude comes to A. So if I multiply by A square root of t, the square root of t will cancel and I'll get amplitude A, which is what I want my signal waveform to look like. So that's the coefficient of S1. And S0, logical 0, is just the negative of S1, so it's the same thing, it's just as a negative sign. So now I have the coefficients in signal space, this one-dimensional signal space, the coefficients of the two symbols for the antipodal signaling. So signal space is of unit dimension. If I look at on-off keying, you know, again, S1 is the same, so the coordinates are the same because these are, you know, they're the same symbols. So of course they have the same representation, the same basis. And the logic 0 in the antipodal and the on-off keying case is just the origin. It's just 0 because we send nothing. So let's start looking at this, you know, one-dimensional signal space. So it's a one-dimensional space, so when I get a received signal, an R of t, I simply take the inner product with the only basis function, one-dimensional. So basically I'm taking a convolution, the correlation of the received signal with basically S1, but this is the factor that normalizes it so that it's really C1 I'm doing the inner product with. And so I see right here the correlator structure very, very clearly. So this is a correlating version. But remember, of course, that I could have implemented this with a match filter if I wanted to. So let's do it graphically. I said what's great about signal space is it gives us a geometric interpretation. So I want to look at the geometry. So I'm going to graph here the two vectors. And it's a one-dimensional signal space, so it's just linear. And S1 has coordinate a square root of 2. S0 has coordinate minus a square root of 2. So one is a vector pointing right, the other one is a vector pointing left. And that's where we get the name antipodal. They point in opposite directions. Next, we could look at the on-off keying. What does that representation in signal space? And of course, S1 is the same. It's the same vector because it's the same symbol and the same basis. But S0 is just the origin, it's a point. So it's a vector of length 0. You know, it's just 1 point. So now I have the signal space representation of these two different modulations. One's an antipodal modulation, one's an on-off keying modulation. Now I want to compare these two. And this is the first thing we have to get used to in the class, is to compare apples and apples, oranges and oranges. So we want to keep the same average energy per symbol. Because in this case, my strategy is to give all the energy to one symbol and none to the second symbol. And this one, I'm really giving equal energy to both. But whether I have one energy budget, and then I can decide who I'm going to give that energy to. But if I want to compare the two, I have to normalize it so that their average energy per bit is the same for both of them. And so that is why we're not going to keep this representation, these kind of coordinates, for our comparison of the performance of these two, that we're going to instead change the units in this space to represent the average energy per symbol, or in the binary case, the average energy per bit. So I have to calculate what is the average energy per bit. So I calculate what is the energy of symbol 1, what is the energy of symbol 0, and of course they both have the same energy in antipodal signaling, it's a squared t. So that means that if I took the average, it would be a squared t. So instead of writing the coordinates here in terms of a and the square root of t, what I'm going to do is I'm going to define this number, which is the average energy per bit, and I'm going to change the units that I'm plotting here in signal space to be units which are average energy per bit. So in this case, if this coordinate was a square root of t, well, that's just the square root of EB, the square root of the average energy per bit. So I'm going to use this second representation. And this is really what we call signal space. Signal space really needs to have a normalization so that all of the coordinates are given in terms of the average energy per symbol, binary average energy per bit. So let's do the same thing in the case of on-off keying. So I start with this representation, but now when I calculate EB, it's very different because one is a squared over t, but the other one is 0. So now the average energy per bit is a squared t over 2. So you can see they were different. They had different energy per bits. So comparing them here would not have been very useful. So what I do now is I do the same thing. I change this coordinate, but now in terms of an EB for this system. So now I come up with S0, and this length becomes the square root of 2 times EB. So this was the energy per bit in this system and this system. Now both systems, when I compare them, it's all based on average energy per bit. And we can see that the lengths look different now. Before they looked like S1 was the same, but then S0 had no energy. But now if I represent them as S0 and S1 in this system being the same length, but in this one it's larger by the square root of 2, then this is a comparison where in both systems the average energy per bit is the same. Average energy per bit here will be EB. Average energy per bit here would be EB because it would be 0 plus 2 EB divided by 2 gives the same energy per bit. So now, when I compare these two representations in signal space, I'll be able to do a just comparison. So, first thing, intuition. Which system is going to have better performance? Better performance in terms of bit error rate. Well, the way to think about it is, what is the separation between the two symbols? Because essentially, intuitively, the farther apart they are, the easier it's going to be to tell them apart. Because the farther apart they are, even when noise is added, it's going to be easy to tell them apart. If they're very, very close, a little bit of noise is going to make it tough to tell which one was transmitted. So I look at these two and I say, what is the separation between the symbols? So I look here and I say, well, the separation between these two symbols is 2 times the square root of EB. But if I look here, this symbol and this symbol, the separation is the square root of 2 times the square root of EB. So therefore, there's larger separation by a factor of the square root of 2 in this system. So just intuitively, by doing this renormalization to the average energy per bit, it becomes clear to me that the antipodal signaling should have better performance because the symbols are more separate. So now what we'd like to do is apply our two rules. So we could have the map rule or the maximum likelihood rule. In the case of the map, it would be to choose the closest with an a priori. And of course, if the map receiver had equally probable symbols, then it would be simply to choose the closest. It would be the equivalent of the maximum likelihood. So let's assume these are equal priors, equally probable symbols, and so it's a map receiver, but I could have said, you know, it's equal to the maximum likelihood because I'm going to assume that the probability of a 0 equals the probability of a 1 equals 1/2, equal priors. So if that is the case, then I know the rule says choose the closest. If I have R and it's, you know, it's a one-dimensional space, so here's my R. Well, this one is closer to logic 1. I'm going to choose logic 1. This could be exactly the same R, and in this case, my receiver would tell me instead to choose S0 because it would have been closer to S0. So of course, the for a given received signal, I might have different conclusions because my hypothesis on what symbols were transmitted were different. So certainly what I can do to simplify my receiver, since my receiver says choose the closest, I could, in this one-dimensional case, send a boundary. A boundary is the midpoint between the two symbols. So the midpoint, if the received is to the right of the midpoint, then I'm going to choose logic 1. If it's to the left of the midpoint, I'm going to choose logic 0. And the midpoint, of course, is at a different location for on-off keying, but both of them give me easy calculations to do to make a decision based on the received signal. So for instance here, if r, the coordinate of the received vector, if it is greater than 0, choose S1. If it's less than 0, choose S0. Now in the on-off keying case, the midpoint is at the square root of EB divided by the square root of 2. So if the received coordinate is larger than this midpoint, I would choose S1. If it's smaller than the midpoint, I would choose S0. So now we're going to go on and calculate the bit error rate. We're going to calculate the probability of error. I'm going to start with the antipodal case. Once I'm done with the antipodal case, we'll briefly go back to the on-off keying case. So I wrote up here the criteria for the decision process for the antipodal case. In the antipodal case, if the received coordinate is greater than 0, choose 1. If it's less than 0, choose S0. So I want to calculate the probability of error. The probability of error is, the law of total probability tells me, it's probability that a 0 was sent times the probability that I make a mistake when a 0 is sent, plus the probability 1 is sent times the probability I make a mistake when the 1 is sent. So that would be the total probability of error. Probability of error if I send a 0, probability of error if I send a 1. Okay, so now what is the probability I will make a mistake if 0 is sent? So that would be, if I make a mistake, that means I choose 1 even though 0 is sent. So when will I choose 1? Well, the only time I'll choose 1 is when r is greater than 0. So what I need here is a probability that r is greater than 0 given that 0 was sent. And this time, what I need is the probability that r is less than 0, that I choose 0 when actually 1 was sent. So this is the law of total probability, which gives us an expression for the probability of error. So the first term for the first situation, and the second term for the second situation, second type of errors. There's like two types of errors. So again, I assumed equal priors for this examination. So equal priors means that P0 and P1 are both 1/2. And now I look at the second part here, and what we have is the probability that r is greater than 0, given that 0 is sent. If 0 is sent, that means that the S1 is minus the square root of EB, because a 0 was sent. But of course, noise is added before I get to r. Now on the second type of error, it's when r is actually equal to the square root of EB. It was a plus square root of EB which was sent. So in both of these cases, it's based on what was sent. I've replaced the s with what was sent. So here I know 1 was sent, so r equals s plus n, but I know what s is. So let's go through the steps here. R is greater than 0 and r is equal to this. Well, that means that minus EB plus n is greater than 0. And in this part, r is less than 0, but r is also equal to this expression. So that's the equivalent of saying that the square root of EB plus n is less than 0. So now if I take these expressions and I isolate n, I get 1/2 the probability n is greater than the square root of EB, plus 1/2 the probability n is less than minus the square root of EB. But of course, if I multiply this by minus 1, it'll just change the sense of the inequality, and these two things are the same. So it's 1/2 of the probability that n is greater than square root of EB, and so I just get the probability n is greater than the square root of EB. And this probability, well, I calculate it. I know the distribution of n. The distribution of n is Gaussian, zero mean, with a certain variance. And so I have it n greater than square root of EB, means the integral of the square root of EB to infinity of this probability density function. So it's quite simple to find the probability of error from this signal space analysis. So we have the result for the antipodal. Now if we looked at the case for on-off keying, it'd be very similar. But before we go on to the on-off keying, let's just look at the antipodal in another way. I'm going to introduce a function that we call the Markham's Q function, which is a function that is found in many textbooks. And it's used particularly in communications. And it's just a name we give for an integral that we see all the time of the density function. So it's the probability that a unit normal zero mean random variable is greater than x. And so this here, the variance is equal to 1 in this definition of the Markham's Q function. So if I take this expression where I have sigma, I can do a change of variables so that I put my sigma actually in the endpoint of the integration. And in that case, I can write this integral in this form. It's just an easier form of representing what is the integral. We define a function which is the integral function. The Q function of the square root of EB over sigma. So very often when we describe probability of error, we're going to write it in terms of this Q function. So Q function of the square root of EB over sigma, and we often use n0 over 2 as our parameterization of the noise. We call the definition of the noise variance as being a power spectral density of n0 over 2, which means that we can plug it into this expression. And for antipodal signaling, we get it's the Q function of the square root of 2 EB over n0. And EB over n0, this is the energy per bit, average energy per bit. And this is the power spectral density of the noise. So clearly this is a type of signal to noise ratio. So finally, the probability of error is a Q function of a square root of a signal to noise ratio, and we have a factor of 2 here in this signal to noise ratio. If we do turn now to the on-off keying case, I won't go through all the math, but it's very, very similar. Our decision process was if the received coordinate was greater than the square root of EB over the square root of 2, choose S1. If it was less than that, choose S0. We do the same development of the math, and we come up with a single probability that n is greater than the square root of EB divided by the square root of 2. So we get, again, an integral, and we get a Q function. And if we simplify it, we get a Q function where, again, we have a square root of a signal-to-noise ratio. There is a difference, though, between the antipodal and the on-off keying case. So in the on-off keying case, we had Q of the square root of EB over n0, but in the antipodal case, we had the square root of 2 times EB over n0. Okay, so I think I changed a little bit the naming here. This was the antipodal, but most often we call it BPSK, binary phase shift keying. And if we think about the line codes that we used, we would also call the S1 of t would be a non-return to 0, right? I said this was the square 0 to t, some amplitude, that was S1 of t. So we could also, if we were going to discuss our results now, it would be, another way to describe it would be it was a non-return to 0, it was on-off keying. On, we send something, off, logical 0, we send nothing. Binary phase shift keying, because here the phase is 0, and here it's pi. That would be another way of looking at it. I'm just trying to throw at you some vocabulary, because these results that we got, we see everywhere. And these results can come under different names. But the important conclusion is that we can see in the Q function the difference in the performance level. There's going to be a factor of 2 multiplying the signal portion of the signal to noise ratio. So it's like our signal is twice as powerful here than it was here. So that was the advantage we saw intuitively, graphically, because the separation is smaller than the separation here. So qualitatively, we expected it to be better. And this is quantitatively how much better it is. What's 3 dB better? So now we're going to plot the results for the probability of error. In the case of bit error rate, it's for binary signaling, it's a bit error rate versus EB over N0, our signal to noise ratio. And this is essentially the Q function, which is being plotted. And we get what we call the classic waterfall curves. So we expect that as the EB over N0 gets stronger, we have a better and better signal to noise ratio, that of course the bit error rate is going to get lower and lower. This is a logarithmic scale, so we can see that it's 10%, 1 in 100 errors, 1 in 1,000 errors, 1 in 10,000 errors, etc. And the EB over N0 is also given in dB. So this is the probability of error for BPSK and Onoff keying. And we can see that there's a difference, and the difference is 3 dB in between the two curves, because they're essentially the same curve, the same Q function. But one has a factor of 2 in it, the other one does not. Now, when I have this classic waterfall curve, the curve that's closest to the origin is the better curve, because that means if I want to get, for example, 10 to the minus 3 bit error rate, with BPSK I can get it here with something like 7 dB, but if I want to get it with on-off keying, it takes 10 dB, 3 dB more to get the same performance. One last observation is that the Q function is used a lot in telecommunications, but in MATLAB you won't find the Q function. What you'll find instead is something called the error function. But the error function is very closely related to the Q function. It's just a different normalization. So if I wanted to get the equivalent of the Q function, I might write a little script in MATLAB that says it's 1/2 minus 1/2 times the error function of whatever the x is divided by the square root of 2. One other thing, this is if you use MATLAB. If you're using a calculator and you want to come up with a good approximation of the Q function, you could use this exponential. For x greater than 3, 1/2 e to the minus x squared divided by 2 is actually a very good approximation for the Q function. So you're depending on the situation, you might want to use this expression with a calculator, this expression with MATLAB, or just look graphically. These graphs are available in many reference books, so you can just read it off of the curve here also.